What is the specific problem that the proposed method aims to solve?
The specific problem that the proposed method aims to solve is the high latency issue in existing diffusion-based image generation models, such as DAL, E2, Imagine, and Stable Diffusion, which require dozens or hundreds of sampling steps, resulting in latency often exceeding 10 seconds and hindering real-time interaction. The goal of the proposed Diffusion 2 GAN framework is to distill a pre-trained multi-step diffusion model into a one-step generator using conditional GAN and perceptual losses. This approach aims to accelerate the model's inference speed while maintaining high image quality, thus improving the user experience in text-to-image synthesis and expanding the potential of the model in 3D and video applications.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method, Diffusion 2 GAN, works by distilling a pre-trained multi-step diffusion model into a one-step generator using a conditional GAN framework and perceptual losses. The algorithm first finds correspondence between noises and images by simulating the ODE solver with a pre-trained diffusion model. Then, it leverages a conditional GAN to map noises to images in a paired image-to-image translation framework. This disentangled approach allows for the benefits of both generative models, high-quality correspondence using diffusion models, and fast mapping using conditional GANs. The algorithm collects a large number of noise-to-image pairs from the pre-trained diffusion model and treats the task as a paired image-to-image translation problem. It utilizes tools such as perceptual losses and conditional GANs to improve training efficiency and distillation performance for latent diffusion models. Additionally, the algorithm introduces ensembled latent LPIPs, a perceptual loss function that operates directly in latent space, enabling better convergence and lower FID compared to other metrics. The method also incorporates a multi-scale conditional diffusion discriminator, leveraging pre-trained weights and introducing single-sample R1 regularization and mix and match augmentation to enhance performance. By following these steps, Diffusion 2 GAN successfully distills the target diffusion model into a single-step conditional GAN model, achieving superior results on benchmarks like COCO 2014 and COCO 2017.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the Diffusion 2 GAN method include 1. Accelerating inference speed while maintaining image quality. Diffusion 2 GAN distills a pre-trained multi-step diffusion model into a one-step generator, allowing for faster image generation without compromising on image realism. 2. Leveraging separate generative models for different tasks. By disentangling the tasks of finding correspondences between noises and images and learning the mapping, Diffusion 2 GAN combines the strengths of diffusion models and conditional GANs to achieve efficient and high-quality image synthesis. 3. Efficient training process. Diffusion 2 GAN demonstrates that training with a regression loss, specifically the ensembled latent LPIPs, can achieve comparable results to more complex distillation methods at a significantly lower compute budget. 4. Improved convergence and performance. The method introduces innovative components such as the ensembled latent LPIPs for latent space distillation and a multi-scale conditional diffusion discriminator, leading to better convergence and enhanced image quality. 5. Superior performance in distillation. Diffusion 2 GAN outperforms other distillation models like UFOGen, MD-UFOGen, DMD, and ADD, showcasing its ability to closely follow the original trajectory of the teacher diffusion model and maintain high visual quality. 6. Enhanced diversity and text-to-image alignment. Diffusion 2 GAN exhibits higher diversity scores and better text-to-image alignment compared to other distillation models, ensuring a broader range of variation in generated images while preserving the noise-image mapping of the teacher diffusion model. 7. Efficient convergence and training speed. Diffusion 2 GAN converges more efficiently than existing distillation methods, achieving superior FID scores while utilizing considerably fewer GPU days, making it a practical and effective solution for image synthesis tasks.
How is the method validated or tested?
The method is validated or tested through a systematic ablation study to evaluate the effectiveness of each component of the Diffusion 2 GAN framework. This study includes comparing different distance metrics for ode distillation training, such as L1, pseudo-Huber, LPIPS, latent LPIPs, and E-latent LPIPs, to determine their impact on image quality. Additionally, the framework is compared with leading one-step generators using standard benchmarks like FID and CLIP, score on datasets like COCO 2014 and COCO 2017. Visual comparisons are also conducted to assess the realism and diversity of the generated images. The training speed and efficiency of the Diffusion 2 GAN model are evaluated by comparing the total number of function evaluations of the generator network during training on datasets like CIFAR10. Overall, the validation and testing process involve a comprehensive analysis of the framework's components, performance metrics, visual outputs, and training efficiency to demonstrate the effectiveness of Diffusion 2 GAN in distilling pre-trained diffusion models into one-step generators for text-to-image synthesis.
What are the results achieved with this new method?
The new method, Diffusion 2 GAN, achieved superior results in distilling stable diffusion 1.5 into a one-step conditional GAN model. It outperformed other distillation models like UFOGen and DMD on the zero-shot one-step COCO 2014 benchmark. Diffusion 2 GAN demonstrated strong performance with just a regression loss, comparable to guided progressive distillation. By leveraging ensembled latent LPIPs and a multi-scale conditional diffusion discriminator, Diffusion 2 GAN distilled stable diffusion 1.5 effectively, exhibiting superior FID and CLIP score over 1-step SDXL Turbo and SDXL Lightning. Additionally, Diffusion 2 GAN was successful in distilling a larger SDXL model, showcasing superior FID and CLIP score over SDXL Turbo and SDXL Lightning, while maintaining high diversity in image generation. The method also showed improved convergence and lower FID, compared to other metrics like MSE and pseudo-Huber loss. Overall, Diffusion 2 GAN demonstrated efficient convergence, enhanced image realism, and improved text-to-image alignment, making it a promising approach for distilling complex diffusion models into efficient one-step generators.
What are the limitations or drawbacks of the method?
The limitations of the Diffusion 2 GAN method include the inability to support varying classifier-free guidance, CFG, values at inference time, the performance being bound by the quality of the original teacher model, and the potential for a diversity drop as the student and teacher models scale up. The method currently simulates a fixed CFG scale and does not adapt to different values during inference, which could limit its flexibility in handling varying text adherence requirements. Additionally, the performance of the model is constrained by the quality of the teacher model it is distilled from, suggesting that improvements in the teacher model would directly impact the student model's performance. Lastly, while Diffusion 2 GAN addresses diversity issues, there is still a risk of a diversity drop as the complexity of the models increases, indicating a need for further research to mitigate this challenge.